If you're interested in astronomy, you've probably heard that this galaxy and this galaxy are going to collide in roughly 5 billion years' time. The first galaxy is our own Milky Way, or at least an artist's impression of it since we can't see it from the inside. The second one is the Andromeda Galaxy, or Messier 31. The galaxies are currently moving towards each other at about 100 kilometers per second, and conventional wisdom has been that they will eventually collide, destroying both spiral galaxies in the process and leaving behind an elliptical galaxy which you can think of like a spheroidal blob of stars. However, new simulations by astronomers from universities in Toulouse, Helsinki, and Durham show only a 2% chance that the galaxies will actually collide in the next 5 billion years. Using data from NASA's Hubble Space Telescope and ESA's Gaia mission, and running 100,000 simulations that included estimates of the uncertainties in the models and the gravitational effects of two other large nearby galaxies, the researchers found that the Milky Way and Andromeda galaxies collide roughly half the time. But those collisions occur in about 8 to 10 billion years. That's super interesting in general, but won't be of much interest to humans, at least those left in this solar system, because that's far beyond the expected lifetime of the Sun. A little less than half the time, the galaxies pass each other by at such a great distance that neither is disturbed by the encounter, and as mentioned previously, just 2% of the time, the previously predicted collision occurs within 5 billion years. This is a super cool result that was published today in the journal Nature Astronomy, and I'll include a link in the description so you can check out the details for yourselves. ESA celebrated its 50th birthday on May the 30th after the agency was created by 10 founding member states on May the 30th, 1975. If you're keeping track, those countries were Belgium, Denmark, France, Germany, Italy, the Netherlands, Spain, Sweden, Switzerland, and the United Kingdom. Since then, ESA has expanded to include 23 member states, 3 associate members, and 5 cooperating states, including Canada, according to a press release from ESA. There have been many successes and achievements in those 50 years. The launch of the first Ariane 1 mission, sending a spacecraft for an encounter with Comet Halley, the launch of the NASA-ESA Hubble Space Telescope, the first ESA astronauts on the ISS, the first ESA mission to Mars, visiting Saturn's moon Titan, and launching JWST on board an Ariane 5. My personal favourite, mainly because I was involved with it, was ESA's Planck mission to study the cosmic microwave background. Of course, there have been a ton of other big missions and successes, and there's a video on the ESA website celebrating the achievements over those 50 years, and I'll include a link down in the description. Japan's iSpace will attempt to land its Resilience lunar lander on the moon's Mare Frigoris at 3:24 p.m. Eastern Time this Thursday, June the 5th. Resilience lifted off on a Falcon 9 January the 15th, together with Firefly Space's Blue Ghost lunar lander. Blue Ghost took a direct route to the moon and successfully touched down on March the 2nd. Resilience took the more fuel-efficient but longer way around and entered lunar orbit on May the 6th. May the 28th, Resilience performed a 10-minute burn to bring it into a circular orbit about 100 kilometers above the lunar surface. iSpace has tried to land on the moon before in 2023, but its Hakuto R lander failed to achieve a soft landing after communications were lost during the descent phase. If Resilience sticks its landing, it'll conduct a raft of scientific experiments on the lunar surface and deploy a small rover called Tenacious. Resilience has already snapped some amazing photos of the moon, as you can see here, and a successful landing will be another big step forward for the ambitions of private companies to explore the moon. iSpace's US subsidiary has a contract with NASA under the Commercial Lunar Payload Services Program to deliver a payload to the lunar surface in 2027 with its Apex 1 lunar lander. You'll be able to watch the landing live on Thursday over on iSpace's YouTube channel starting around 2:24 p.m. Eastern Time. Our models of planetary formation around stars are still incomplete at best, but astronomers using the James Webb Space Telescope have gained new insights into how the planet WASP-121b formed around its star. WASP-121b is a bit of a hellscape, a giant planet about the mass of Jupiter that orbits its star at a distance of just 4 million kilometers in 1.25 days. The side of the planet facing the star is at a toasty 3000 Kelvin, or almost 5000 Fahrenheit, while the night side is at a cooler but still melting 1500 K. The dayside temperature is high enough that elements such as iron, magnesium, and silicon could exist as gases and theoretically be detectable using spectroscopy. Unfortunately, the observations would need to be done in the UV, as that's where the strongest spectral lines are. To avoid that, the researchers used JWST to measure the atmospheric amounts of water, carbon monoxide, and silicon monoxide on the day side of the planet, and methane on the night side. By using well-studied key ratios like the one between carbon to oxygen for Jupiter-like planets, the astronomers can estimate the amount of heavier elements present in the planet when it formed. The results published in the journal Nature Astronomy show that WASP-121b likely accumulated most of its gas in a region where water was frozen but methane existed as a gas. In our solar system, this would correspond to the region somewhere between Uranus and Jupiter. The planet would also have accreted most of its heavier elements from pebble and rock-sized materials during this phase. Gravitational interactions with other bodies in the fledgling solar system would then have caused WASP-121b to spiral in close to its star. A second group of researchers have built 3D atmospheric models of the planet to explain the differences in composition between the day side and the night side of the planet, and those results are published in the Astronomical Journal. I've just scratched the surface of this research here, and there's much more to learn. You can find a great article over at phys.org, and there's a link to both papers in the description. The detection of a giant planet around a small star has astronomers puzzled. In yesterday's video, we talked about WASP-121b, a Jupiter-like planet orbiting a star a little bigger than our Sun. But did you know that most stars in our galaxy are actually much smaller than the Sun? Astronomers have just announced the detection of a gas giant planet TOI-6894b around a small red dwarf star, TOI-6894. The star has just about 1/5 of the mass of the Sun, and the planet that's been detected is similar in size to Saturn, although only about 50% as dense. The discovery of this transiting giant planet in data from the Transiting Exoplanet Survey satellite is very surprising because it was not thought that such a small star would be able to host such a massive planet. The most popular model for planetary formation is the core accretion model. A planet first forms a core that eventually becomes massive enough to accrete gas and form an atmosphere. This process then continues as the planet accretes more and more gas, eventually becoming a gas giant like Jupiter or Saturn. The problem here is that smaller stars are supposed to form from smaller disks of material, so there's less stuff to accumulate into a planet and less gas to accrete. So how do we get TOI-6894b? The observations have some clues that might point the way to solving the mystery. The planet appears to be much cooler than typical gas giants with a temperature of just 420 Kelvin compared to 1 to 2000 Kelvin for a typical hot Jupiter-type exoplanet. According to the astronomers, this indicates the atmosphere of the planet is dominated by methane and may contain detectable amounts of ammonia. It'll be super interesting to see how our models of planetary formation evolve to explain TOI-6894b, and the good news is that follow-up observations of the planet with JWST are already scheduled and should give us even better insights into what's happening. By discovering such a wide variety of planets around other stars, our understanding of how planets and solar systems form is growing fast.